You can see up here. That is what's called a cubic function. Okay, would anyone like to tell me what kind of function it is? There are two types that we looked at last lesson. Would someone please put a hand up and tell me what it is? Mr. Spalding, what do you think it might be? It is a one-to-one function. How do I know it's a one-to-one function?
Because if you put a line going up through it, it only intersects once at any point, and if you put a horizontal, it only intersects once at any point.
That's right. One-to-one functions, if I was to do a vertical line, it should only hit the graph once. And if I was to put it in a horizontal line, it should only hit once as well. So here, well, that's the base template of every cubic function. This is what we refer to as cubics. So yeah, cubics. All right. So that is a cubic graph. So the next one underneath, I've got a big old minus sign. Now, if we were to use our terminology from what we have for parabolas, how would I describe this negative x cubed in comparison to the first graph? Put your hand up if you can tell me what the specific term is. Jordan at the back.
Is it inverse?
It's not inverse, Mr. Daniels.
It's reflected in the x-axis.
That's correct. This has been reflected in the x-axis. If it was inverted, it would actually look like it was on its side. So this is reflected in the x-axis.
Okay.
So we've got x minus 1. You'll notice that we're here. Can anyone please tell me, put their hand up if they can tell me in words, what is the transformation of this graph compared to the original? Compared to the original. So what's the transformation? Mr. Daniels, how would I describe that?
It's been translated to the right.
But, yep, this has been translated 1 unit to the right. Now you might be wondering, how do you work that out? So with parabolas we refer to its turning point. Well, cubics don't have, or this particular form of cubic doesn't have a turning point. Its stationary point, which is here, it's actually got a very special name, and it's called a point of inflection. And the reason is, it's the point where we've got the 2 points, so it's not like a big turning point where it's, where we are graphing like it's going down or going up. We've got a stationary point here, which is called the point of inflection. And basically, it's a turning point that's stopping for a bit and then keeping on going in the same gradient. So yeah, it's a stationary point. That's the middle point of that graph. And if we look at the next funky ones don't have a feasible transformation to describe them, but they are looking kind of funky. Okay? So, when we draw graphs, we start from left and go up, especially positive ones like this. So you'll notice each of these is referring to an X-intercept. So this one is going here, because that says x plus 2 up there, so that one is referring to this x-intercept here. This x minus 1 is referring to that x-intercept there. What does this x up here refer to? The middle, yeah, so that's the x-intercept here. Okay, so that's the middle one there. So that's and we'll look at practicing how to sketch these very shortly. So for example, for this page that we're going to look at sketching, I would suggest that you would have some sort of ruler-like device, preferably a ruler. Whilst I've got your attention, Mr. Daniels, what would be the x-intercepts of these lovely friends?
I'm going to say that one of them is -1.
Yep.
That another one of them is +2.
Yep.
And another one of them is +3.
Yep. So what I would do to sketch this graph is what I would go, that looks like about a -1. That looks like a +1. That looks like that will be about +3. And then what I would do is I would just go, so that's literally the level of accuracy. The only thing that I would add to this is I'd find a Y-intercept. How do you find a Y-intercept? Yeah. So that would be equal to 0 plus 1 times 0 take away 2 times 0 take away 3. So this would be 1 times negative 2 is negative 2 times negative 3, so that's going to be positive 6. So there we go, 0, 6 is my y-intercept. And that is the level of accuracy required at a year 10 level.
That's incredibly accurate. Extremely accurate.
And so, for the next one, now you'll notice it's got a big minus sign. So this will change where we do our whale noises, or from what point. But nonetheless, the X-intercepts are still the same. So this would still be at 2, 0. This would be at 3, 0. This would be at 4, 0. And we may as well find where our Y-intercept is whilst we're here. X equals 0. So that's going to be 0 minus 2, 0 minus 3, 0 minus 4. So negative 2 times negative 3 is equal to what? 6. 6 times negative 4? Negative 24 times by negative 1? Yeah, so it's positive 24. So it's 2, 3, and 4. So we started from the bottom with a normal one. Of course, with this one, we start from the top. There we go. I didn't do the whale noises. You could do that in your own hand.
Trust me, we were.
I'm sure.
Wait, what's a whale? Is that like it goes? Wait, what's a whale?
I'm glad that I wasn't the only one who heard that too. I think what was supposed to be the question was, what does a whale noise sound like?
Someone said whale. Wait, is somebody doing
What is, I think it's a philosophical question. What is a whale? Now listening up, please. So there, for this next one here, this is going to be one of those strange squared ones. But again, that's going to still be an X-intercept here, X-intercept there. And we get negative 1, positive 2, Y-intercept. So an X is 0. So it's equal to 0 plus 1, 0 minus 2 squared. What's negative 2 squared? 4 times 1? Thank God nobody said 7. I would not be in the mood. So remember, the squared repels the line. So this one will look like this. And then it will repel the line like that. Because that's what the squared does. It turns it into a quadratic, and it will go and change the shape of it to move backwards.
The square represents the hypothetical turning point.
Yeah, so this is in fact a turning point, yeah. And for fun fact fans, that is what we call in the business of methods a local minimum.
Why is it local?
The reason why it's local because it's not absolute minimum. Absolute minimum would be negative infinity because it keeps going down that way. But it's a local minimum that within the sketch of the graph, that would be the lower turning point. So that's why it's called a local minimum. And this friend here would be the local maximum, if there's a, which you don't really need to know at year 10 level, but it's always nice to know a little bit of extra stuff.
What level is that for?
That's year 11 or year 12.
Fun to know.
Is that to do with, you know, how we do maths and the graphs?